Welcome to TalkTensors.
Yeah, welcome everyone.
I am your host, and as always, we're here to bridge the gap between the bleeding edge of machine learning research and the practical reality of building intelligent systems.
That's the goal, right?
Yeah.
We're not here to just skim the abstract.
Exactly. We're here to tear the paper apart, to look at the architecture and really understand what makes it tick.
Yeah, we treat this deep dive kind of like a dinner party.
A very nerdy dinner party.
Yeah, right, where the guests just happen to be the most intelligent researchers in the room. So we assume you know your gradients from your Hessians. We're going to skip the basic jargon where it obscures the point and just double down on the intuition.
Today, we are looking at a paper that I think fundamentally changes how we think about the relationship between large language models and physical control.
The big one.
It really is. The paper is titled Eureka, Human-Level Reward Design via Coding Large Language Models.
And frankly, it is about time someone attempted to solve the dark art of reinforcement learning.
The dark art. I love that phrasing.
Yeah.
I want to pause on this dark art characterization immediately, because if you're listening to this and you haven't explicitly trained a robot in, say, Isaac Jim or Mujoko.
You might think, well, how hard can it be, right?
Right. You want the robot to walk, so you just give it a point when it moves forward.
It sounds so trivial.
It does. It sounds like basic conditioning.
But if only it were that linear. I mean, in Super Mario, the score is literally on the screen. It is extrinsic and explicit.
You stomp a Goomba, you get points.
Exactly. In robotics, the score is this dense mathematical function that you, the human, have to hallucinate.
Hallucinate is the perfect word.
You have to invent the metric of success from scratch.
And the issue isn't just defining the ultimate success, Ryo. It is shaping the behavior leading up to that success.
Yeah.
That is where the real pain lies.
Precisely. Let's look at the credit assignment problem, which is really the fundamental headache here. So imagine you have a robotic hand with, say, 24 degrees of freedom.
That is 24 individual motors.
24 motors moving maybe 60 times a second.
Right.
If after 5 seconds of just random wiggling the hand accidentally rotates a pen perfectly, you give it a +1 reward.
But the optimization algorithm,
The PPO, yeah.
but the PPO algorithm looks back at those 5 seconds and asks which specific motor twitch caused the +1.
Exactly. And it has absolutely no idea.
Because so much happened.
Right. Maybe it was the wrist rotation at T-2 seconds, or maybe it was the pinky finger twitch at T-4.
Or just random noise that happened to a line.
Yeah. If you only reward the final outcome, what we call a sparse reward, the robot effectively learns nothing.
It's like trying to learn to play the piano by only being told if you played the entire concerto perfectly at the very end.
With zero feedback on the individual notes.
Exactly. So you get zero feedback for months, and then a 1 on the final day. That is not a learning curve.
No, that's a cliff.
Which is impossible to learn from.
Which is why researchers do reward shaping. They don't just reward the goal, they reward the progress toward the goal.
They write a Python function.
Yeah, a function that says reward equals 1.0 times velocity plus 0.1 times upright posture minus 0.05 times energy usage.
And that right there is where the dark art comes in. Because who decided that upright posture is worth exactly 0.1?
Right. Why not 0.5?
Why not 0.001? Why is velocity weighted 10 times higher than posture?
Nobody knows. It is purely intuitive.
It's guesswork.
I have seen PhD students spend 6 months just tweaking those coefficients.
Change the numbers.
Yeah. They run a training job for 3 days. The robot learns to walk, but it jitters uncontrollably.
So they lower the energy penalty.
They lower it, they run it again, and now the robot just falls over and slaves because that saves the absolute most energy.
The game of whack-a-mole. You fix the jitter, you break the walking. You fix the walking, you break the energy efficiency.
It feels significantly less like science and a lot more like alchemy.
And the paper actually validates this struggle with data. They surveyed RL researchers, and 92% admitted to using manual trial and error to design these functions.
92%.
But the damning stat, the one that really highlights the inefficiency of our current workflow, is that 89% of them knew their final reward function was suboptimal.
They just gave up.
They ran out of patience or compute and just settled for good enough.
So the premise of today's deep dive, this Eureka paper, is that we stop doing that. We stop tweaking coefficients by hand.
Instead, we treat reward design as a code generation problem.
Exactly. The core thesis here is that large language models, specifically GPT-4 in this context, have become proficient enough at writing code that they can not only write a reward function for a robot, but they can debug it, optimize it, and evolve it better than a human expert can.
And strictly speaking, we aren't just talking about a one-shot prompt here. We aren't just going to ChatGPT and saying, hey, write me a reward for a walking robot.
No, Eureka is an agentic loop.
It writes code, runs the simulation, looks at the failure, and then rewrites the code. It is evolution.
It is evolution accelerated by GPU physics. And the results are just startling. They tested this on 29 open source RL environments, everything from quadrupeds to dexterous hands.
And Eureka outperformed expert human-engineered rewards on 83% of those tasks.
83%.
That is a landslide. And we're going to unpack exactly how it achieved that. We need to look at the architecture because there are 3 specific design choices here that make this work.
Environment as context, evolutionary search, and reward reflection.
Let's start with the input. Environment as context. How does Eureka actually know what the robot looks like?
This is the first brilliant design choice. Usually when people try to use LLMs for robotics, they describe the robot in natural language.
They just type it out.
Yeah, they say I have a 4-legged robot with 12 joints.
That looks like a dog.
Exactly. But that is incredibly vague. Looks like a dog doesn't tell the LLM the variable names for the joint velocities. It doesn't tell the LLM the coordinate system of the hip actuators. So Eureka doesn't use natural language descriptions of the robot at all. It feeds the raw environment source code directly into the context window.
When you say source code, are we talking about the C++ backend or the Python wrapper? Because if you feed C++ into a context window, you're going to burn tokens so fast.
No, they feed the Python interface code from Isaac Jim. It's the class definition.
Okay.
So the LLM sees class and inherits from vectask. It sees the init function. It sees self.obs buffer, which contains the observation buffer.
Why does that matter, though? Why not just tell the LLM the robot has 4 legs? Why do we need the actual class definition?
Because 4 legs is semantically rich, but syntactically useless.
Ah, I see.
If the LLM tries to write a reward function using robot.leftleg.position, but the actual variable in the code is self.docpos index 3, the code just crashes.
Right, it won't even compile.
Exactly. By feeding it the raw class definition, the LLM performs what is essentially static analysis.
So it acts like an IDE, an integrated development environment. It sees the variable names, the data types, the tensor shapes.
Exactly. It sees that self.docpos is a tensor of shape, num_ems by 12. So when it writes the math, it knows to use PyTorch operations that match those exact dimensions.
This is why they achieve such high zero-shot compilability.
Right.
The paper mentions that the code compiles on the first try a vast majority of the time, which is crazy for AI-generated code.
And that's not because GPT-4 is a genius at physics. It's because the prompt engineering removed the ambiguity of the API. It constrains the solution space to valid Python code that fits that specific environment class.
That seems so obvious in hindsight, but it's a huge shift. You aren't translating reality into English for the LLM. You're giving the LLM the code that defines the reality.
And that allows for zero-shot generation of executable code. Because the LLM sees the API, the first draft of the reward function is usually syntactically correct.
It actually runs.
It runs. It might not be a good reward yet, but it compiles.
Okay, so we have the context. The LLM writes a Python function called compute reward. But as you said, the first draft might be bad.
Usually is.
It might incentivize the robot to just stand still and vibrate, because that minimizes the energy cost.
Or it might create a local optimum where the robot falls over immediately.
Why would it do that?
Because the penalty for falling is smaller than the penalty for trying to walk and failing over a longer period.
Oh, wow. So it just gives up instantly to minimize the penalty.
Exactly. This is where the second pillar comes in. Evolutionary search.
Walk us through this. This isn't just asking GPT-4 to try again, is it?
No, Eureka samples a batch of award candidates. In the paper, they use a batch size of 16. So it asks the LLM to write 16 different reward functions based on the same prompt.
16 independent attempts. Why 16? Why not just one and iterate on that?
Diversity. LLMs are stochastic, right? If you ask it once, you get one idea. If you ask it 16 times with a high temperature setting, you get 16 very different approaches.
So maybe one focuses on velocity, one focuses on distance, one tries a logarithmic scale.
Right. Then it takes all 16 of those functions and runs them in parallel in a simulator, in this case, Isaac Jim.
This is a crucial detail, right? Because you couldn't do this with real physical robots.
Absolutely not. Isaac Gym runs directly on the GPU, so it can simulate thousands of robots at once without moving data back and forth to the CPU. It trains a policy for each of those 16 rewards simultaneously.
We were talking about simulating millions of steps of physics in just a few minutes.
Precisely.
So we have 16 different universes running in parallel, each trying to learn a task with a slightly different definition of success written by the AI.
Exactly. And after a set number of epochs, Eureka looks at the results. It evaluates them against a fitness metric.
And it throws away the rewards that didn't work.
All right. It keeps the best ones. And then this is the evolutionary part. It mutates them. It asks the LLM to take the best code from generation 1 and improve it for generation 2.
It's natural selection for software, survival of the fittest code. But here is the part that I think is the real breakthrough.
Yeah.
In biological evolution, mutation is random. A cosmic ray hits a DNA strand. But Eureka isn't mutating randomly. It is performing intelligent mutation.
That is the third pillar, and frankly, the crown jewel of this paper. Reward reflection. This is the secret sauce.
Let's get into it.
You see, usually in evolutionary algorithms, you just know that candidate A scored 50 points and candidate B scored 10 points.
You don't know why candidate A won.
Exactly. You just breed candidate A and hope for the best.
But Eureka constructs a textual feedback loop.
Yes, it looks at the training data from the simulator. It doesn't just look at the final score. It looks at the individual components of the reward function it wrote.
Let's make this concrete for the listener.
Yes.
Suppose the AI wrote a reward function that has two parts, a reward for moving forward and a penalty for falling down.
Okay, perfect example. Eureka looks at the logs after the simulation. It sees that the moving forward component is 0. The robot isn't moving.
But the penalty for falling down is also 0 because the robot is standing perfectly still.
So the robot found a loophole. If I don't move, I don't fall.
Now, a standard genetic algorithm would just see a low overall score and kill that candidate.
Right, but Eureka passes these statistics to the LLM and asks for a reflection.
So the LLM analyzes the numerical logs.
Yes. It generates a text summary. It literally writes out the velocity reward component is 0. The fall penalty is 0. This implies the agent is engaging in safety-seeking behavior and not exploring.
Wow.
The penalty for falling is likely too high relative to the potential reward for movement.
So it translates the numerical failure into a paragraph of English explanation. It diagnoses the root cause.
Yes, and then it feeds that paragraph back into GPT-4. It says, here's your previous code. Here's what happened. The robot is too scared to move. Fix it.
And GPT-4 effectively goes, I see. I need to lower the penalty for falling or boost the reward for velocity to make the risk worth taking.
Or it might change the functional form entirely. The paper shows really cool examples where the LLM decides to wrap a variable in a torch.x function.
An exponential function.
Yeah, to make the gradient steeper near the goal. Or it adds a threshold. It performs targeted editing based on a semantic understanding of why the robot failed physically.
That is the agentic part. It is reasoning about the learning process itself. It's debugging the curriculum, not just the code syntax.
It creates a closed loop where the error signal is natural language. That is a very powerful concept.
Because it bridges the gap.
Right. It bridges the gap between high-level reasoning, like I want the robot to run, and low-level implementation, like I need to increase the coefficient on the hip joint velocity by 0.5.
It's performing chain-of-thought reasoning on the optimization landscape itself.
And the paper shows that without this step, if you just tell the LLM, the overall score was 20 try-again performance drops by nearly 30% on average.
30%.
And it's much worse on the hard tasks. The why is essential. The LLM needs the semantic bridge to understand which part of the Python code is responsible for the physical failure.
It's like having a senior engineer looking over your shoulder. The senior engineer doesn't just say, fix it. They say, you're ignoring the z-axis, look at line 14.
Exactly. And sometimes the fix isn't just changing a number. As we said, the reflection leads to structural changes, changing the shape of the reward manifold based on the reflection.
I want to move from the theory to the practice, because all of this architecture is nice, but does it actually work on things that matter?
Right, the real-world benchmarks.
I want to talk about the hero task of this paper, the pen spinning.
The shadow hand pen spinning task. This is really the Mount Everest of robotic manipulation and simulation.
Describe the setup for the listener who hasn't seen the video. Why is this harder than, say, making a bipedal robot walk?
Okay, so you have a shadow hand. This is a robotic hand that closely mimics a human hand. 5 fingers, 4 joints per finger, very complex kinematics.
And you have a pen.
And you have a pen. The goal is to spin the pen continuously around the fingers like a drummer spinning a drumstick or a bored student in a lecture.
And this is difficult because of the contact.
Right. It involves rapid contact switching. The pen is constantly breaking contact with one finger and making contact with another. It is dynamically unstable.
So if you are off by a millimeter.
Or a millisecond, the pen just flies out of the hand. In walking, you have the ground. The ground is stable. Here, the object you are manipulating is free-floating and reacting to every micro-tremor of the fingers.
And the paper claims that manual reward engineering just failed here.
It was incredibly difficult. Previous attempts either couldn't do it at all or they required using demonstrations.
Which is motion capture.
Basically, yeah. Motion capture of a human doing it, which the robot then tries to mimic. But Eureka solved it from scratch.
No human motion capture data.
Zero. Just the physics and the goal.
How? Did it just guess the perfect equation on the first try?
No, and this is where the evolution part really shines. It used curriculum learning. Eureka was smart enough, or rather, the architecture allowed it to break the problem down dynamically.
Wait, did the researchers explicitly tell it to break the problem down into steps?
No. That is the beauty of it. In the early generations, the rewards that survived the evolutionary cut were the ones that just taught the hand to reorient the pen.
Just hold it and turn it a bit.
Yeah, turn the pen to 90 degrees. Turn the pen to 180 degrees. These were simpler tasks that the initial policy could actually learn without dropping the pen.
So it learned the absolute basics first.
Right. Once the policy learned that Eureka took that pre-trained brain and started fine-tuning it with a new reward function specifically generated for continuous spinning.
So it essentially wrote a lesson 1 reward function, trained the robot, then wrote a lesson 2 reward function.
Exactly. And the result is a simulated hand spinning a pen at rapid speed. It is mesmerizing to watch the video.
And remember, the authors didn't explicitly program a curriculum.
Eureka's generated rewards facilitated that transfer when set up in that pipeline. It evolved the teaching method alongside the student.
That is incredible. And that brings us to the broader stats. They tested this on 29 environments, 10 different robot bodies.
Quadrupeds, quadcopters, cabinet opening arms.
Right. And Eureka beat the human experts on 83% of them, with an average normalized improvement of 52% over the human baselines.
It absolutely dominated. And they compared it to other language to reward baselines too, like L2R.
How did it compare there?
Well, L2R uses rigid templates and predefined primitives. Eureka writes freeform code, which is vastly more expressive. Eureka dominates L2R, especially in these high-dimensional dexterity tasks where templates just fail completely.
But there's a specific chart in the paper that I found absolutely fascinating. The correlation chart.
Ah, yes, the novelty analysis. This is where the paper gets a little unsettling, philosophically speaking.
So they looked at the reward functions Eureka wrote, and they compared them to the reward functions humans wrote for the exact same tasks.
They calculated the correlation, basically asking, is the AI rewarding the same things the human was rewarding?
And for the easy tasks like bouncing a pole, the correlation was high.
Right. The AI and the human both agreed, keep the pole straight. That's obvious. Physics is physics.
But for the hard tasks?
For the hard tasks, specifically the high-dimensional dexterity tasks like the pen spinning or the cabinet opening, the correlation dropped.
It dropped significantly.
In some cases, it was weakly correlated or even negatively correlated.
Negatively correlated. That implies the AI was penalizing things the human thought were good, or rewarding things the human thought were bad.
Yes.
And yet the AI's policy is performing better. How is that even possible?
It really comes down to the difference between semantic logic and gradient dynamics.
Explain that.
So humans write rewards that make sense linguistically. I want the hand to be close to the pen, so I will write reward equals negative distance.
Logic 101. Closer is better.
But to a neural network, optimizer distance is a really harsh metric. It might create a gradient that is too flat, or it might have local minima where the hand gets stuck hovering near the pen but not actually touching it.
So it's close, but it's not manipulating it.
Right. So the AI looks at the math through its evolutionary search and says, forget distance. I am going to reward the change in velocity relative to the root joint.
Which makes no semantic sense to us at all.
None. Why reward velocity if we want position? But mathematically, that velocity term might provide a stronger, smoother gradient that shoves the policy toward the pen faster than a distance metric would.
It is finding a wormhole in the optimization landscape.
Exactly. It's an alien reward. It works, but we don't understand why it works intuitively. It found patterns in the physics engine that human intuition entirely missed.
It effectively removes the human bias from the learning process.
It does. And that raises a massive question about alignment.
It certainly does. If the AI is optimizing for alien rewards, how do we know it is doing what we want? What if it learns to open the cabinet by smashing it?
That is the perfect segue to part 3, alignment and human feedback. Because the paper directly addresses this. They have a section on RLHF without gradients.
Reinforcement learning from human feedback. Now, usually this involves training a separate reward model to predict what a human would like.
Which is expensive, complex, and requires thousands of human labels.
Eureka does it differently. It does it in context.
Yeah.
This brings up the duck walk story. I love this story because it is so relatable.
Yes, the duck walk. So they were training a humanoid robot to run. They gave Eureka the overarching goal: run as fast as possible.
When Eureka did what it does best, it optimized.
It optimized perfectly.
Yeah.
And the result was a robot that ran weirdly.
It was crouching. It was doing a literal duck walk.
Low center of gravity, super stable, very fast.
Mathematically perfect.
But aesthetically terrible.
Yeah.
If you were a roboticist, you would look at that and say, no, that is not running. That is sputtling.
So how did they fix it? Did they have to go in and write a new mathematical equation for torso height? Did they derive the kinematics?
No. They just typed feedback into the Eureka loop. A human looked at the video of the robot duck walking and typed, the agent is too low, make it stand upright.
That's it. Just natural language.
Just natural language.
And Eureka read that feedback.
It read the feedback as part of the reward reflection step. It ingested that complaint. And in the next generation of code, it automatically injected a completely new variable.
Without the human telling it how.
Right. It looked at the root states tensor, found the z-coordinate of the torso, and added a reward term for maximizing that z-coordinate.
So it translated stand upright into self.rootStates index to greater than target height.
Correct. It modified the reward function code on the fly based on a semantic complaint.
And the next iteration.
The robot stood up and ran normally. The user didn't need to know the variable name, they didn't need to know the math or the PyTorch syntax, they just stated their preference.
This is a huge democratization of robot training. You could have a non-expert, a factory foreman, looking at a robotic arm and saying, hey, stop swinging your arm so wide you're going to hit someone.
And the system adjusts the reward code to penalize wide swings on the y-axis.
It essentially turns the reward function into a user interface.
The code becomes the medium of communication between the human intent and the robot's policy. It patches that alien logic we talked about with human preference.
And they also tested human initialization, right? Because sometimes humans do have good ideas to start with.
Right, we shouldn't throw the baby out with the bathwater. Humans are actually very good at knowing what matters. Distance matters. Rotation matters.
We're just bad at the coefficients.
Exactly. We don't know if the weight should be 0.1 or 0.001.
So the human int mode lets the human write the first draft.
You write your best guess. Reward distance plus rotation. Eureka takes that human code as generation 0. Then it evolves it.
And how did that perform?
The paper shows that this collaborative approach often yields the best results of all. It beats Eureka from scratch, and it definitely beats the human alone.
It's the cyborg model. Human architect AI contractor. We draw the blueprint, the AI lays the bricks, and handles the actual physics optimization.
Which is likely the future of this entire field. We define the constraints and the safety boundaries, the AI optimizes the implementation.
I want to get into the technical analysis now. They did some ablation studies. They tested GPT-4 versus GPT-3.5.
Which is a critical comparison.
Does this only work with the smartest frontier model?
They found that GPT-4 is significantly better. The gap is very noticeable. GPT-4 writes bug-free code more often, and its reflections are much more insightful.
But GPT-3.5 wasn't a total failure.
No, surprisingly, GPT 3.5 still performed comparably to humans on many of the tasks.
That's interesting.
It shows that the architecture itself, the evolutionary loop, the feedback mechanism is highly robust. Even with a quote-unquote dumber coder, if you give it enough tries and good feedback, it eventually converges on a solution.
But GPT-4 is the clear winner for complex tasks.
Definitely. It understands the physics context better.
And what about the reward reflection? We touched on this, but How critical is it really? What if we just turn that off?
If you turn it off, performance falls off a cliff.
What if we just give the AI the numerical score? Just say you got 50 points, try again.
They saw a nearly 30% drop in performance on average, and much, much worse on the harder tasks.
So it proves that the why matters.
Just knowing you failed isn't enough. You need to know how you failed to fix the structural code. The semantic summary of the training dynamics is the key that unlocks the LLM's reasoning capabilities.
Let's talk limitations. The paper's very honest about them. What can Eureka not do?
The biggest limitation is the dependency on the fitness function.
Let's define that for the listener.
The fitness function is the ground truth. It is the ultimate metric of success. For pen spinning, is the pen spinning. For walking, it's velocity. Eureka needs this overarching metric to know which reward candidates to keep and which to kill.
So if I can't mathematically define success, Eureka can't evolve a reward function for it.
Exactly. If the task is fold the laundry neatly and you don't have a mathematical definition of neatly.
If you can't express neatness in a tensor.
Right. Eureka struggles. It relies on having a queryable ground truth to evaluate its candidates. It cannot invent the goal. It can only invent the path to the goal.
And the other limitation is simulation versus reality.
Right. This entire pipeline relies heavily on Isaac Gym. Isaac Gym is a massively parallel simulator. It runs thousands of robots faster than real time. That is how Eureka can evaluate 16 reward functions in just a few minutes.
You cannot do that with physical robots.
No, you can't run 16 physical robots for 10,000 hours in 5 minutes. So Eureka is currently bound to simulation.
To use this in the real world, you need a robust sim-to-real pipeline.
You train in the matrix and hope it transfers to the real robot. The paper mentions this works well for the walking robot, but for complex high-dexterity things, sim-to-real is still a massive hurdle.
But historically, looking at the big picture, this feels like a major pivot point. We have gone from code as policies, where the LLM directly tells the robot move arm left, to code as reward.
Where the LLM writes the textbook for the robot to learn from.
Exactly.
It moves the LLM up the abstraction ladder. Instead of being the pilot, the LLM is the flight instructor. It's designing the curriculum.
Which allows the low-level policy to be a standard neural network.
Which is much faster and more reactive than an LLM, while the LLM handles the high-level logic and strategy offline. It brilliantly combines the best of symbolic AI writing code and connectionist AI neural networks.
So what does this all mean for you, the listener, if you are building agents, if you are working in automation today?
It means that if you are manually tuning parameters, you are doing it wrong. We are rapidly entering an era of auto-tuning everything, whether it's reward functions, hyperparameters, or even system architectures.
If you can define the goal and provide a feedback loop, an LLM can probably optimize the configuration better than you can.
And it means that our ability to describe a task in natural language is becoming the primary programming skill. The syntax is handled by the machine. The intent is the human contribution.
The prompt is the new source code, but the reflection is the new debugger.
I love that. The reflection is the new debugger.
Okay, we've unpacked the paper, we've seen the stats, we've seen the duck walk. We understand that feeding raw Python code into the context window is the key to grounding. Now it's time to get a little speculative.
My favorite part.
It is time for Novel Notions.
Let's do it.
Quick disclaimer for the listener. The following segment is for entertainment purposes only. These ideas are outlandish extrapolations based on the paper's architecture.
Outlandish, but plausible.
Right. All right, concept number 1. I am calling this the physics breaker discovery agent.
Ooh, physics breaker. Tell me more.
So we saw in the paper that Eureka found rewards that were negatively correlated with human intuition. It found hacks or alien strategies to maximize the reward.
Right, like the robot that learns to vibrate to gain energy from a physics glitch in the simulator?
Exactly. Usually in robotics, we consider those bugs or cheating.
We try to patch them out.
But what if we invert the goal? What if we apply Eureka to scientific simulation? Let's say we have a complex simulation of protein folding, or a new material, or even a theoretical physics model.
Okay, I'm following.
We set the fitness function to violate the laws of thermodynamics or maximize energy output beyond input.
Oh, I see.
We tell Eureka, write a reward function that incentivizes the agent to find edge cases where the simulation physically breaks down.
You use it as an automated anomaly hunter?
Yes. Instead of trying to make a robot walk, you are trying to make the simulation crash or behave impossibly.
Yeah.
Eureka evolves agents that are essentially QA testers from hell.
They hunt for the floating point errors, the boundary conditions, the places where our theoretical models fall apart.
Exactly.
That is fascinating. It's an adversarial Eureka. You aren't optimizing for performance, you are optimizing for falsification.
You could use this to stress test entirely new scientific theories.
Here is my mathematical equation for a fusion reactor. Eureka, try to break it.
Exactly. If Eureka can't find a reward function that breaks the model, your model is highly robust. If it does break, it hands you the generated Python code and says, here is exactly how I broke your physics.
That is a brilliant application of the alien reward concept.
Yeah.
It leverages the AI's total lack of bias. A human wouldn't try to vibrate the simulated atoms at a specific bizarre frequency because that shouldn't do anything.
But the AI tries it and boom, it finds a hole in the theory.
I love that.
All right, concept number 2. This one is a bit more Black Mirror. I call it the recursive reality trainer.
Recursive reality. Sounds ominous.
So Eureka uses code to shape robot behavior. It writes a game, essentially the reward function that the robot plays to learn a skill.
Correct.
What if we use it on humans?
Go on.
Imagine VR training. Let's say for a surgeon or a pilot or even a tennis player. You are in VR. The system observes your physical movements. It sees you are failing.
Okay.
Maybe you have a duck walk equivalent in your tennis swing. Your elbow is dropping too low. Instead of a generic tutorial popping up on screen saying, raise your elbow, Eureka generates a custom minigame in real time. It writes a new reward function for your VR environment.
Oh.
Maybe it spawns literal lava on the virtual floor that only hurts your avatar if your elbow drops.
It gamifies your specific error.
Yes. It creates a unique ephemeral game rule that only exists to fix your specific bad habit. It uses reward reflection on your psychomotor data.
Users is dropping elbow. Generate a game mechanic where dropping elbow equals severe penalty.
And as you improve, the game evolves. The lava disappears. Now maybe it introduces a new visual challenge for your wrist rotation.
It's a personalized, procedurally generated curriculum that evolves in real time based on your physical data. The teacher isn't a pre-recorded human. It is a code-generating loop that modifies your reality to shape your behavior.
It's inverse Eureka. Instead of shaping the reward to fit the AI agent, you shape the virtual environment to train the human agent.
That would be incredibly effective and potentially highly addictive. Imagine an educational video game that rewrites its own code continuously to keep you exactly in the optimal flow state.
That is the dream. Or the nightmare, depending on who writes the overarching fitness function for the human.
Indeed.
Well, on that recursive note, we are going to wrap it up. This paper, Eureka, is a masterclass in agentic design. It shows us that when we give LLMs the keys to the compiler, they can unlock capabilities we didn't even know were possible.
It really is the end of manual trial and error and the beginning of automated algorithmic discovery.
I couldn't agree more. For you listening, the deep dive into the source material doesn't have to end here. Think about what your fitness function is in your own workflows and whether an agent could optimize it for you. Keep your gradients clipped and your rewards dense. This is TalkTensors signing off.